Okay, now we continue with context diagrams. The first part we looked at how to model architecture using UML, visually model. We also look later on how to model it textually. Then we talked about architecture description languages. But actually also an important issue is the so-called context diagrams. So we can represent the architecture, the internal structure, but it's also important to so architecture lives in some environment. So context diagrams are used to visualize this, the relation with the environment. So this is the case. Every system has an architecture. I should maybe, the screen is not optimized, right? Maybe that can. So every system has an architecture, we said, is composed of elements and relations among them. How to model the context. The context is the environment, so this, which it inhabits. Okay? So how to model the relation between the architecture and the environment. That is important because before you start the architecture, the system, you have to know where it is located. Also, if you are dealing with very large systems, so typically your system will also interact with other components, and you have to actually visualize this. So context diagram is a good means for that. It defines what is in and what is out of the system under construction, based on the architecture. So in the middle you will have architecture. This actually is the first ingredient, the first element that you show to the stakeholders. You say, so this is typically your system, and it is in this kind of environment. Okay? So it basically shows how it interacts with the outside world. The entities in the outside world, so outside world here means external to the system that you are going to develop. What could that be? Could be humans, computer systems, physical objects, etc. So anything that is outside of your system, for which you are not responsible to design it, but you have to interact somehow with these entities, they are called the context. So it's typically like this. So you have a system, kind of black box, and you have to know the relations with the environment. In a pure context diagram, that's important, you don't specify the internal details, but you just show your system as a black box. Because your concern in context diagrams is not to represent the architecture itself, but just the interactions with the environment. Okay? But sometimes people also show the internal structure, so that you have more detail about the interactions. Context diagrams do not show any temporal information, so you don't show the interactions, the order of interaction or data flow, or the conditions or constraints under which the data is transferred, etc. So it's just a very simple diagram actually. How do you represent a context diagram? Typically in the middle you just put your system. Okay? This is the key, this is your system, and you define all the entities which will interact with your system. As we said, could be human beings, hardware, etc. Another complex system, okay? But you are only responsible for designing this. And here you visualize, actually you provide the map. So this is the environment, the context. Okay? And in the context you define the interactions Here's just two, in this case you have two relations. This means, so double relation means interacts with, and single arrow means like data flows from X to Y. This could be also more refined, but the bottom line here is just what are the external entities. Here we have 5. What is the interaction with the system? Okay. So actually this is the first thing that you actually also show. This is the thing that we are going to design. This will be these are the external entities, and we are responsible for designing this. Okay, context diagram. In the project you have also to define such a context diagram. This is an example from your textbook. This is about science data processing segment. It's the system. It's quite, and there are several entities which will interact with that system. And here in this case it's shown what the interaction is. Okay. This is one way to do it. In UML, if you would UML, you actually have seen it. What are context diagrams? I've just shown it, right? What is actually typically a context diagram? It means to represent context. Use cases there. It actually does not have an explicit mechanism for representing context diagram, but we know use case diagrams. What are use case diagrams? This also defines actually the system. It defines what is in the system, what is outside of the system, what are the entities that are outside of the system. The actors, right? Actors can be again human beings, devices, complex software, etc. So if we say I want to just use case diagram, so this is not a notation in UML, but if you want to stick to pure UML, then you could use case diagrams in which you define just the rectangle, which will be your system, and you define the actors outside of your system, the entities which will interact with your system. Like here, so patient monitoring system, and here we have two entities which are human beings, patient and nurse, and there's also an external system, the patient log. Typically this could be maybe a database, right? But by defining this, you say I'm only responsible for this. I will design this. So this will be outside. And my system will interact with patient and nurse. Okay, so it gives where is your system located? How does it interact with your environment? Quite simple, right? So two ways, just the informal notation like this, or the use case diagrams you can use. So we can now summarize the whole modeling. Every system has an architecture. It's better to make this explicit. Some people would actually react to this. What do you mean by every system has an architecture? In our project we don't have an architecture, but here we mean like every system. If you have lots of code, it has some internal, the architecture is already implicit. There's some structure in it. And if we say, and we have to describe it, then you make it explicit. If you don't make it explicit, you will lose all the benefits of architecture. Guiding process, guiding the project, defining your design decisions, defining rationale, means for communication among stakeholders, right? So we make it explicit, we get all these benefits. But to make it explicit, people tend to go for informal notation. They draw boxes and lines. This is the architecture. Put it in a document, and and actually expect that they also gain the benefits. Sometimes it gets even worse, okay, because you get lots of misunderstandings. So it has a few limitations. It's usually ambiguous, open for multiple interpretations. So we need to represent it more precisely. For that, software architecture can be modeled textually or visually. Textually, architecture description language, which will be the next topic, or visually. If we take visual approach, we can use UML. Okay. It makes sense. It's quite strong motivation for looking at UML because it's a de facto standard. All the tools are using UML, etc. So if we go for that, there are three approaches as is, using extension mechanisms or introducing new notations. Extension mechanism typically using stereotypes. Then we said, okay, to define the environment, a system by itself actually is not standalone. It's always in some environment, which means it interacts with some entities in the outside world. So the context diagrams are a means to represent this, to visualize this. Questions about this part? It's clear, right? Okay. Well, then we go to the next one. Just start here. Good. That's the second. So we can represent UML architecture visually or textually. Okay. We go for textually, which means we define textual representations, and we talk about so-called software architecture description languages. I will first shortly look at motivation for ADLs, a short summary on components, and component-based development, because most architecture description languages also refer to the notion of component. We will look at some example ADLs and look at comparison of ADLs based on some research paper, and look at ZADL, XADL but pronounced like ZADL, which is one of the latest developments. So this is the case, the dimensions, architectural description, system as architecture we have to describe, can visually or textually. Textually is architectural description languages. There are many, actually it's also ongoing research. Many ADLs have been actually introduced in the last 10 to 15 years. Okay, it's also quite an active domain in the architecture design community. The key motivation for ADL, why do you need a textual approach? Okay, we said already, if you take visual, it could be understandable, right? We can just visualize and etc. But here the key motivation was that, like, although we have now more precise modeling notations, the key motivation for using ADLs is that many diagrams are still ambiguous. On the other hand, we don't want to actually represent the architecture as programming language because they are too low level, but the architecture is really at the highest abstraction level. Okay. So we need something to describe the architecture in a precise way, but not as programming. So for that purpose, ADLs provide a precise but an abstract description. It is precise like programming languages, but it's also abstract. There are also other benefits for ADLs, we will see. It supports actually the analysis of the system, can be used for code generation, etc. But typically the first motivation was that the many diagrams are ambiguous, so people were searching for more precise modeling techniques. Okay. So this different ADLs have been described in this paper from Nenad Medvedovic and Richard Taylor, a classification and comparison framework for software architecture description languages. The paper is well, about 10 years ago, I don't know, but it provides a survey on the existing ADLs and compares these ADLs, architectural description languages. These are the languages which are listed in this paper, which are also known in the architecture design community: ACME, Adage, Aesop, Darwin, Meta-H, Rapida, SADL, Unicode, Write. For example, this one supports the definition of new architectural styles, also has an interconnection language, an exchange language. This supports description of architectural frameworks for avionics, supports use of architectural styles, has been introduced Darwin for analysis of distributed message passing systems, Meta-H for real-time avionics control systems, for simulations, SADL formal base for architectural refinement. This is for heterogeneous component and connector types, and Write supports formal specification and analysis among architectural components. So, already started in 93, or earlier yet, even earlier, but it's about 10 to 15 years ago, and still some new ADLs are being proposed. So if you look at these ADLs, just compare all these ADLs, which is also one of the observations in this paper, then we see that they seem to focus on three elements: components, connectors, configurations. This is not a surprise for us, because we said architecture consists of components and connectors and represents the gross level structure, configuration. Right. Components represent primitive building blocks. Connectors are the mechanisms, the relations among these components. And configuration refers to rules for combining some components. So this could be one configuration or composition of these components. So all these ADLs focus on these three elements. What is an ADL? It's explicit modeling of components, connectors, and configuration. So here the idea is explicit is important. ADL is not a programming language, as we said, but aims at the higher level of abstraction, higher level design, the highest level design. Okay. But it's like, if you look at the spec, it feels like a programming language. So you have keywords, textual keywords, component, connector, configuration, style. Okay. But it's not a programming language, but it explicitly models these architectural elements. We should also differentiate ADLs from other languages. Like, it's not just like high-level design notations. It's not module interconnection languages, object-oriented notations, programming languages, or formal specification languages. So it's dedicated means to represent architecture. Explicit representation of architecture. Well, this is a more refined look at configuration languages. We could have actually three types of configuration. Implicit, so you have a system, which defines some of the configuration, but the configuration information is here in the implicit one. It's distributed, okay, across the definitions of individual components and connectors. And it's implicit, it's not explicit. It's nowhere described. Inline configuration languages, they specify it actually explicitly, but the connections are inline. Okay, you don't have specific language for that. Explicit is actually at the level of ADLs. They model both components and connectors separately from configurations. What are advantages of ADL? One of the key motivations was actually to be more precise, less ambiguous, which is by the motivation for architectural modeling. Okay? But ADLs is also ADL is also a key motivation. But besides of that, so besides a formal way of representing architecture to make it more precise, it is intended to be both human and machine readable. Okay? Supports describing at higher level of abstraction. This we have actually discussed. But also it permits analysis of architecture. Okay? Usually if you have textual representation of your architecture, it's easier to analyze the non-functional requirements, the quality, okay, or completeness, consistency, performance, concurrency. Okay? And further, ADLs can support automatic generation of software system. If you have textual representation of architecture, you could have some transformation which can provide more refined, which can refine the architecture to produce the detailed design. Actually, then we enter in the domain of model-driven development, where everything is a model, and where we have transformations, and where the code is automatically or semi-automatically transformed. Okay. So that's these are the benefits of ADLs. You could say, okay, one thing is like, of course, people could prefer visual, because it's visual, you can understand and see it. But there are also obvious reasons also for using textual representations, among which analysis and maybe refined or automatic generation is also an important issue. Okay. Okay. This ADL, the concept should be clear, I hope. Just textual representation for representing architecture, components, connectors, configuration. One of the key issues here is, of course, components. This is the definition from our textbook. The software architecture of a program or computing system is the structure or structures of the system which comprise software components, the external visible properties of those components, and the relationships among them. So the software components is an important issue in software architecture design, in particular ADL. This is a book from Clemens Sapersky about component software, one of the first books on component-based software development. What's a software component? A unit of composition with contractually specified interfaces and explicit context dependencies only. So independently deployable unit of execution. Software component, independently deployable, and can be subject to third-party composition. We know what objects are, what's a component. I think this has not been discussed before, right? Components, if we compare these two, components versus objects. Components are just at a higher level of abstraction. Okay, it's actually the next level of abstraction. Components do not share state. They are at higher level of abstraction. Objects have state. One of the key issues was actually in object-oriented design that objects should have their specific state. Components do not have that. Components have a more extensive set of communication mechanisms. In objects, we have message passing, right? But components can be more extensive. Okay? A relation and communication mechanism could even be a middleware. Okay? An RPC, right? Broadcast, publish, subscribe. Okay? Components are often of larger units of granularity than objects and have complex actions at their interface. Typically, a component can also be viewed as a collection of objects in which, so internal details of a component in which the objects cooperate. Okay. Components often use a persistent storage, whereas objects have local state. Components are deployable entities. You can put them in the system, deploy it, and then it's executable. Components are usually language independent. So you could have 2 or 3 components in the same system, but the implementation could be with different language. That's the idea. So it's all related to actually reuse, software reuse, where we see software as a composition of components, like we see normal artifacts, like composition of components. And for that, we need to have independently deployable units of composition. To be independently deployable, a component should have a clear distinction from its environment and other components. A component must have also clearly specified interfaces, and the implementation must be encapsulated. So what are the interfaces? Okay, it's components at higher level of abstraction, typically includes set of objects. It has provides interface. It defines the service operations that are provided to other components. This is a component. It has, okay, provides, I can press on it, right? And requires interface. Defines the service that specifies what service must be made available for the component to execute as specified. What's the requires interface here? If we take this example, this is the provides, right? I can push buttons. If you look at this as component, what's the provides? Is there a provides requires interface? There's a requires interface, right? I tried to find it. It's the battery, right? You should put a battery in it. Just an example. Interface, component, requires interface. Just the same idea. Requires interface. I should plug this in, otherwise we don't have this screen. Provides interface. I can push the buttons. Same idea. Oops. And components are persistent and stable. Okay. Second. That's the component. So if this meta-model component consists of interfaces, a required interface, provides interface, interface includes operations, operations can have parameters. Okay. Well, a bit about semantics of components. So the idea is that you have to compose these components to produce some system. For that, actually, we have to know how the components work, and typically for each component, besides of the interface, also contracts are specified. Contract includes the invariant, the global constraints that should be valid, preconditions which need to be met by the client to use the component or use the operations, the interface of the component, and post conditions which the component promises to establish when it's deployed. Okay. It's about, so while composing these components, we could have different types of incompatibilities. Parameter incompatibility, where operations have the same name but are of different types. So you want to click them, but somehow the parameters do not fit. Operation incompatibility, where names of operations in the composed interface are different. Okay. And operation incompleteness, where the provides interface of one component is a subset of the requires interface of another. It's just the same similar notion of components in general. So if something doesn't fit, we say it is an interoperability problem. Incompatibility problem, sorry, not interoperability, that's different. What is component composition? So we have a library of independently deployable units, and we use this library to compose this system. That's called component composition. The process of combining, assembling components to create a system. So this involves both the integration with each other, but also integration with the infrastructure. Typically you have to write also glue code here. And as we said, there are also constraints for this component composition. One of the key concerns is, of course, that when composing the components, the contracts should be actually respected. There are different so-called component models, definition of standards for component implementation, documentation, and deployment. Examples of component models: EGB, COM, Corba component model. Probably you have seen them also before. Component model actually specifies how the component and the interface should be defined. In UML, if you look at UML, the way to represent the components, we will also look at how it's represented in ADL, but this is in UML. These are the alternative ways to represent the components. So there are actually three ways. This is in UML2. As you can see, it can be used like stereotype, or a kind of rectangle and then a component, or both. The lollipop represents interface, or provides interface. Like here, this order, it's a component. It has two interfaces: order entry, account payable. Interface consists of a set of operations, and this socket notation provides defines a requires interface. Okay, like provides, these are lollipops, and sockets. Besides of that, there's the notion of port. It's a named interface, defines a set of operations and events that are provided by the component or that are required. For example, here is a port, order entry. Okay, this is a provides port, and this is a requires port. So the whole composition, this is from the UML spec. This order component product. As you can see, these interfaces are just clicked. So the provides interface of product meets the requires. In that way, these two are composed. So far about components. In general, component-based development. Independent deployable units. And if you look at ADLs, also they use the same notion of component or similar notion. Let's just look at some examples. What time was the break? 25? 30, okay, great. This is one of the earliest ADLs developed at Carnegie Mellon University's general purpose ADL with emphasis on analysis of communication protocols. It actually builds on CSP, a process algebra, so uses variation of CSP to specify behaviors of components, connectors, and systems. It has tool support, so it's not easy to find from this, but how does it look like? That's all. I will not discuss this in detail. There's a complete PhD thesis about this, but we are more interested in what does it mean to have an ADL? Okay, what's it like? But typically, this is an ADL specification in Write, in the Write architecture description language. So you can see this. So it has some keywords: system, component, connector, instances, attachments. So we are now representing, or in this case, a simple client-server architecture using a Write architecture description language. In textual representation, there's no visual representation here. This system appears to have two components, which one is called client, the other is servers. Component has a port, which has send request, and server has a receive request. The connector is RPC, remote procedure call. Connectors can have roles, so keywords. One role is called caller, the other role is called callee. This is the formal spec, or what it means, how to combine these. And there's some glue code to combine these. Here's the attachments, the client server, the client send request. The send request, that's the port, is attached to RPC caller of this. So no need to look at the details. I will not explain this, but the idea is like, so we have to model the architecture. We can do visually, but we want to do it. We can also do it textually. Why? Because it's more precise. That was one of the key motivations. But also it can be used for analysis and for further refinement. This is how an ADL spec looks like. Unicorn is another example. Usually the same mechanisms pop up. That is, so what did we say? ADLs consist of components, connectors, configurations, etc. And in all these ADLs, we typically see the keywords component, connector. Like also in Unicorn, developed by Mary Shaw et al. At Carnegie Mellon. Here we have a component sort, which has an interface. Again, we have a connector, etc. In Unicorn, it's specific. It also provides specific component types. So you could have module, computation, shared data, and connector types. But the principle is typically the same. Okay, you define the means to represent the components and means to represent connectors, means to define the composition and constraints. Koala is another one. It's from the Netherlands, developed by Philips Consumer Electronics for modeling of architecture of embedded systems. Koala is an architectural description language, but also a component model you can say for development of embedded software for consumer electronics, so like TV. Okay. Also, the idea was so you have a large repository of components, and these systems are just built using these components. This is an example of the Koala components. Like here, this is from the representation of a TV. Component TV platform. It has two interfaces: provides interface, requires interface. This is actually partial specification of this part is actually visualized here. Like here's a component CTV platform. That's the component. It has provides interface, which is called PPRG, which is here. Okay. And requires interface. It has two: slow and fast. Okay. It contains components C front end, CTunerDriver. So this part actually only represents this, right? And it defines a mechanism to connect these components. So connects PPRG. So that's this one. PPRG connects to CFRE. That's the component front end to the PPRG. Okay. There's a full specification of Koala and all these other languages, but we will not discuss that in detail. The issue here is just to show you examples of what ADLs are, what it means to represent architecture in a textual way. I think let's break at this moment, and then we continue in 10 minutes.